we left off last time. I think we were talking about the integrator last time, and we said that this integrator circuit ideally does not have this resistor in the feedback, right? Ideally, the current flowing through here is equal to what? What is the current equal to? The current flowing through the resistor. What is it equal to? Forget about this RF here. It's this V input divided by this resistance, right? Since this is, assuming this is a DC value, then this is a DC current. This DC current comes into a capacitor. Capacitor is an open circuit basically for DC, right? So it's like having, an open circuit here, or for DC quantities, the output voltage will then be what? Yeah, the output is RF divided by R, 1 plus SC times RF, right? That's for the case where I have a resistor in parallel with the capacitor, right? So if I don't have a resistor in parallel with the capacitor, we have a DC current coming into the capacitor. So let me redraw the circuit. So the circuit will look like this: minus, plus, and this is R. This is, what is the current we said here? VI divided by R. So VI divided by R is also flowing here. So it's VI divided by R flowing here. So voltage output is equal to, so this is V output, current flowing this way. So voltage drop across the capacitor is in the opposite direction. So this plus this equals 0 because I have feedback, and the difference between these two nodes is 0, right? So V output is equal to minus VC, and VC is equal to, since we know the relationship between IC and VC is equal to IC is equal to C dVC by dt, right? So VC is equal to 1 over C integral of IC dt. VC is equal to 1 over C integral of IC dt. And then IC is equal to what? VI over R. So it's the voltage across the capacitor. So it's minus. So V output is equal to minus VC. So it's 1 over RC, right? Integral of IC dt, right? That is the output. So I'm basically going to integrate the current, right? So the integration of the current is going to be the output scaled down by some RC value, right? So in this example here, find the output produced by a Miller integrator in response to an input pulse voltage of 1 volt, duration 1 millisecond, width, and then their RC values are given. So given RC values, and they tell you that the input voltage looks like a 1 volt DC for 1 millisecond, right? If the integrator capacitor is shunted by 1 mega ohm resistor, how will the response be modified? So let's go back here first. Now what we derived a few minutes ago was with the case with the capacitor only. What happens when we add the resistor? What happens when we add the resistor? What happens when we add the resistor? So in the case of the capacitor only, we derived the output voltage equal to minus RC, integration of I, and assuming I is a DC value, so let's say I input, right? So it's the integration of 1 times T, which is T, right? From 0 to some time T, right? So this looks like what? Sorry, a ramp, but with negative ramp. Do we agree? We're okay with this? So it's a negative ramp, right? So now they're telling you that I am putting a pulse that has a duration of 1 millisecond and a height of 1 volt. That's my input voltage, right? So what do we expect the output to be when the output is during this time? Up to 1 millisecond. What do we expect the output to be? With a capacitor. Only capacitor, no resistor. Assuming capacitor has the zero initial condition, what is the output gonna look like? It's gonna behave like what it's governed by this, right? The output is governed. This is the output-input relationship. This is the output versus an input-current relationship. So I have an input voltage of 1 volt, and I'm given the value of the resistance. So I'm gonna take my input voltage as 1 volt divided by the value of resistance that I'm given. I will get some current. This is 1 volt. I will get some input current. This input current is a fixed, it's a DC current. This DC current will flow into the capacitor. So the output relationship, the output will look like this. This is my DC current, which is the 1 volt divided by the resistor. And this is my RC, time constant, due to the, the equations that we derived. So it's going to look like what? Up to 1 millisecond, the output will look like? No, why attenuate? I didn't. It will until 1 millisecond. It will be a ramp, right? What happens after 1 millisecond? The voltage became 0. So if the voltage becomes 0, then the current becomes 0. It will go back to 0. Ideally, right? If there is no resistor here.
Don't you say, oh, there's no resistor?
No resistor. The case of only the integrator, pure integrator, right? So in the question they told us, find the output produced by Miller integrator, ideal Miller integrator to an input pulse of 1 volt and with 1 millisecond. Let R be 10 kilo ohms, C equals 10 nanofarad. If the integrator capacitor is shunted by 1 mega ohm resistor, how will the response be modified? So we first want to look at the response without the shunt capacitor. And then we want to look at the response, so without this RF. And then we want to look at the response with RF. So the response without RF is what we derived, just an integration. So we put a fixed DC value, we integrate based on this equation, we get a negative ramp, right? Yes? No?
If you talk about the...
No, not okay. Not okay.
So
Yes?
the shape of this resistor, would you say that it will either attenuate to positive or negative because of the DC gain?
Shape of this resistor?
Like the shape of this amplifier
Yeah?
because of the resistor?
No, I removed the resistor now. I removed the resistor.
Yeah,
Do we all agree about this?
But before removing,
Yes, ma'am.
I don't know how did you get the V naught is equal to
Okay.
function of time.
Okay. Okay. Plus ground R C here. It's plus minus V out. This is plus minus V input. Okay. So this is the ideal integrator, C, and this is R. I have current coming into the ohm path. What is this current equal to? VI divided by R. This is, let's say, a DC value. VI is a DC value for now. Okay. So if it's a DC value, this is always going to be VI divided by R. This is an ideal op amp, so the current will flow up here into the capacitor, right? If it flows this way into the capacitor, there's a corresponding voltage drop across the capacitor this way, and this is V output. Since I have feedback, then the difference between these two is 0, this is 0, then this is 0, right? This is 0, then this is 0, which means that V output is equal to minus VC, right? So since this is 0, then V output plus VC is equal to 0, so V output is equal to minus VC, okay? So what is VC equal to? from your capacitor, from your understanding of capacitors, the current flowing through the capacitor is equal to C dVc by dt. VC, the voltage across the capacitor, which is what we are interested in, is equal to 1 over C integral of IC dt. This is VC. IC happens to be what? Just happens to be VI over R. So 1 over RC, and then it happens to be DC. It happens to be a DC value.
Is the capacitor not initially charged?
Capacitor is not initially charged, yes. So it happens to be a DC value. So this, I can take also my V outside. This is my VI over R. That's the current. I took it outside, right? This is the current. It's VI divided by R. I took it outside. I also had a C outside, so I kept it outside here, right? That's not VC. This is V output. This is my V output.
So the integration of the current will give you VI RC.
Sorry, excuse me?
The integration of the current.
Integration of the current. What is the current?
It's
The integration of the
VI.
current is VI divided by R. Both of these are fixed values, so I take them outside the integration.
Okay.
Right? So what am I left inside the integration? 1 times dt. Integration from 0 to t, which is equal to VI divided by RC times t. I bring that here with a negative. So it's equal to negative VI divided by RC times t. So it's a constant times t. So it's a ramp, but negative, with a negative slope. It's a slope, but no y-intercept, right? So this is the slope, negative ramp. Right? Okay? So this is the case, with the capacitor. How about if I put the resistor in parallel? What
Then the
happens?
current will
It will
divide.
keep going.
If RF is very, very, very big, we know it's going to reduce to this. We know that. This is what it's almost going to look like. But if RF is not big, small, reasonably small value, what happens still? Let's go through the same logic, right? What's happening at the input? Did the input change? The input is not changing. So I still have a DC current equal to VI over R flowing into what now? Not the capacitor anymore. It's flowing into capacitor resistor combination. RF and C. Right? What happens after a very long time to a capacitor? This is DC current. This is DC current VI.
So it will
This is a DC current VI over
become an
R.
inverting amplifier.
right? So if I keep this DC current flowing into this combination for a long time, the capacitor will become an open circuit, and the voltage and this current will flow through the resistor only, right? So it will sort of tell me what's the value of the final voltage across this combination, right? Do we agree? Assuming if I keep this on for flowing into this combination for a long time, capacitor will become open circuit eventually, and initially its current will flow in the combination resistor and capacitor, right? It will flow through both, and then after a transient response, capacitor will charge, increasing its voltage until what? Some maximum voltage. What is this maximum voltage equal to in this case? Some V output, V across this R, equal to what? Equal to VI over R flowing in this RF. That is the output voltage, final output voltage here. Right? That's the final output voltage when? After many time constants. These are certain time constants. After many time constants, I will reach an output voltage equal to VI times RF or of VI times RF or over R. VI times RF over R. That's my final voltage after many time constants. Right? But now my pulse, now go back to this is general case, right? My pulse that I'm putting in now is 1 millisecond only. So my job is to say, okay, after 1 millisecond, what's happening? So in the case without a resistor, after 1 millisecond, the voltage is brought to 0. So what happens to the output? Without a resistor still. Without a resistor, after 1 millisecond, I bring the voltage to 0. So the output voltage will be back to 0. This is the case without this resistor. Okay? How about the case with the resistor? Right? That's what we need to look at. The case with the resistor, we said, we derived it last time in class. We said that it looks like this. This is the general transfer function case with the resistor RF in the feedback. What does this look like? Single time constant, low pass filter circuit. Right? With a DC gain of minus RF over R and omega naught or break frequency equal to C over RF. 1 over CRF. Right? So it looks like a low pass filter. Right? So if you have a ramp, it will slow down the ramp because a ramp has certain frequency. A ramp, again, it's assuming this ramp is going to be periodic, for example, right? A ramp, if you have a periodic ramp, it's a function that is non-sinusoidal. I can analyze it using Fourier series, chop it up into a number of sine waves. These sine waves, if I add them up, I can create this ramp somehow, right? So if it's a periodic waveform made of these sines, then it means it will have frequency content. This ramp will have frequency content, right? Or the square that I'm putting in will have frequency content, right? This square that I'm putting in a square, I'm not putting in a ramp, right? So I'm putting in a square waveform. This square waveform, if I did not put this resistor, the output was a negative ramp. Now I'm putting this resistor. What will the output look like? The output will be acted upon by this transfer function, right? The output is equal to this transfer function multiplied by the input, right? So this transfer function will now take my square wave, chop it up into these many sine waves, right? The sine waves have some high frequencies and have some low frequencies. What did we say this looks like? My single time constant what? High pass or low pass? Single time constant, low pass. Exactly. This looks like my single time constant low pass filter with DC gain minus RF over R, or gain, I'll call it RF over R, and break frequency here, omega naught equal to 1 over tau, which is 1 over CRF. That's this, right? So if I put in a square wave, right, what's going to happen to it? That's the question. When I put a square wave without this resistor, the square wave looked like this. Try and keep the gain outside. It was a negative ramp. Now I put the square wave and I'm adding some frequency dependence now to the circuit by making this look like a low pass filter. This looked like a low pass filter with a omega naught somewhere here. What's going to happen? Obviously, I will not have these sharp rises. I will be eliminating them, and I know that they're going to be eliminated since even with RF very large, I get a ramp. So if RF is very large, what happens to omega naught? Yeah, so RF approaches 0, right? So it's like having an integrator only, right? So at DC, it has a very high gain, right? And at high frequencies, the gain is attenuated with a constant minus 20 dB per decade. A square wave has many, many frequencies, right? This rise here has many, many frequencies. These frequencies were all attenuated. Sorry, these frequencies are all going to be attenuated. So anything above DC is going to be attenuated. How about anything that is DC? Anything that is DC will pass through with a certain gain, right? This gain we were able to find the relationship between input and output with respect to time by looking at the current through here, etc., etc. Right now, I have this square wave. How do I figure out what the output will look like? what did we do? When we had the capacitor alone, what did we do? We had to find the currents, and we looked at the current flowing through the capacitor, and we did the integration, find the relationship between output and input by doing the integration of current flowing through the capacitor to find the voltage, right? So we will have to do the same. But now I have a resistor in the circuit, yeah. So it's like the transient analysis stuff that you did in 214. So let's look at what we need to do. Like, do you see that? Do you agree that these transfer characteristics, or the body plot, is an indication of what's going to happen? So to any frequency component going into the amplifier and then coming out, not to the full signal, because now unless it's a sine wave, right? Remember I think we did an example where we had several sine waves with different magnitudes and frequencies going through one of the examples, and we looked at the values of the input and we looked at the values of the output. Now I don't have a sine wave coming in, I have a square wave. This square wave is many sine waves. So you cannot just say, okay, I will look at it and I will know what's coming out. Right? If you take this square wave, fine, and chop it up into all its constituent sine waves, bring each one of them in, you will know what's going to happen to each one of them at the output. That's okay. But if you do not do that, then it's impossible to be able to look at to figure out what the output is without looking at the transient response or the time domain transient response that you did in 214. I hope it becomes clear now. So actually, let me derive it first. So the case where I don't have the resistor in the feedback, we derived, right? So V output is equal to what? Minus 1 over RC, integration of 1 times dt, right? That's what we derived. And if you substitute with R equals 10 kilo ohms and C equals 10 nanofarads, right? So just substitute RC here, and then T is 1 milliseconds. You will get minus 10 times T. Is everybody okay with this at least? So, V is 1. V is 1. V is 1. Okay? So I agree, sorry. V is 1. Okay? So between 0 and 1 millisecond, this is the case. Everybody is fine with this.
But they didn't plug in at T equals 1 millisecond.
No, they did.
They integrated from 0 to T.
They integrate from 0 to T, but they said that this equation is only valid from 0 to 1 millisecond. That's what they're saying here. Okay? So if you plug here, then they plug with it. Then they plug it. So it reaches a magnitude of minus 10 volt at T equals 1 millisecond. So then they plug the equation. So it's V output is equal to minus 10 times T. V output T is equal to minus 10 times T. And then when they substituted with T equals 1 millisecond, then they calculated that the output is equal to minus 10 volts. Right? So at 1 millisecond, the output is negative 10. Fine with this? Okay. So now we need go back here. 1 millisecond. Minus 10 volts is the output. This is time. This is the output. Okay. Equals minus 10 volts. Yes. So T is 1 millisecond. T is 1. Okay. So if that's the case, now let's see what happens in the other case. So in the other case, we said what's going to happen. We said that the input looks very similar, meaning I have a current here that is DC equal to 1 volt divided by the R that they gave me, that is flowing through my feedback circuit, RF. So what are the values that they get? And then this current is equal to 1 volt divided by what? 10 kilo ohm? 10 kilo ohm, right? 1 volt divided by 10 kilo ohm. 1 volt divided by 10 kilo ohm, so that's 10 to the 10 to the third here. So it goes up as, right? So 10 to the fourth, sorry. 10 times 10 to the minus 3. 10 times 10 to the minus 3. So it's 1 over 10 to the fourth. It goes up as what?
0.401.
Which is what? Huh?
1.
0.1 milliamps, right?
No.
Why not?
4 zeros. 0.4 zeros and 1.
0.123.
4.
Is it 4?
Yeah, 4 zeros.
10 to the
No, 3.
3 zeros.
Milli.
Yeah, 3 zeros.
milli.
3 zeros and amps. That's the current.
So it's 1 milliamp.
So it's 1.1 milliamps. That's 1, 2, 3. So 0.1
Okay.
milliamps. That's the current flowing in here,
That's a lot.
right? So that's the current flowing due to 1 volt divided by 10 kilo ohm resistor, right? The feedback resistor is equal to what? That they plugged in. They said that the feedback, if the integrated capacitor is shunted by a 1 mega ohm resistor, right? So the feedback resistor is 1 mega ohm. So this is 1 mega ohm. We said that if I keep, so this is 1.1 milliamps flowing here. We said that if in steady state the capacitor will be open circuited. So I know that after a very long time, this capacitor voltage will be what? This current multiplied by 1 mega ohm, right? So it's 0.1 milliamps multiplied by 1 mega ohm. That is equal to what? I divided by R. I times R is equal to what? 100, right? So that's going to be 100 volts. So the final voltage for this combination is 100 volts. So is this, when is this gonna, when is, if I just, again, this has nothing to do with the op-amp yet, right? This is just my transient response stuff from 214. If I put a DC current through an RC circuit, what's gonna happen to the output voltage? We know that the output voltage across the capacitor will look like what? This. We know that from transient response in 214. The initially current will flow in the combination depending on the impedance of both, right? Until the capacitor reaches its steady state voltage, it's fully charged. If it's fully charged, the voltage across the capacitor is equal to the voltage at the input, and it's going to oppose any current flow, right? It's going to oppose any current flows. This value of voltage is what? It's going to be 100 volts, right? When does this happen? When does it reach 100 volts? From 214. When does it reach 100 volts? At a long period of time. So this long period of time we call, typically this long period of time or periods of time related to RC circuits, we sort of quantified them using them time constants, right? We said that after one time constant, the voltage, you remember 214, after one time constant, the voltage was so and so. After two time constant, the voltage so and so. After three time constant, after 6 or 7 time constant, the voltage reached a steady state, right? So after many time constants, the voltage will reach 100 volts. So I want to know what is the time constant of my circuit now. What is the time constant of this circuit? RC, right? Which R? This 1 mega ohm. Which C? The C value is 10 nanofarads. 10 nanofarads. What's 1 mega ohm times 10 nanofarads?
Wouldn't that be 10 to the
10 to the negative 2, so it's 0.01 seconds or 1 millisecond, right? Which is bigger? This or this? Sorry, not this. This is, no, this is, I'm talking about the time, sorry, the 1 millisecond. This is what? This is 10 milliseconds. 0.01, 1, 2, 3, yes, it's 10 milliseconds, sorry. So 10 milliseconds versus what? Versus my square wave ended when? At 1 millisecond, right? So my square wave was until 1 millisecond. My circuit time constant here, that would bring my voltage across my capacitor to minus 100 volts, right? Or voltage across the capacitor to 100 volts, meaning the output voltage would be minus 100 volts, is 10 milliseconds. Okay? So did I reach that time? No. Which means that the voltage across the capacitor is lower. How much lower? Then you have to find the time domain expression. That, time domain expression for voltage across this circuit. You remember that the transient response, the time domain expression, the general format was K0 plus K1 e to the minus t over tau. That was general form for that. We need to figure out how to calculate that for this circuit. So let's see. So I will redraw this, my resistor and capacitor. And this is 0.1 milliamps, right? 0.1 milliamps. And this is 1 mega ohm. And this is 10 nanofarads. 10 nanofarads. The time constant was 10 milliseconds for this circuit. My input pulse was only up to 1 millisecond. And my V final V across the capacitor is minus 100 volts. This is at steady state, after 10 milliseconds, right? So we never reach that. We're going to reach something else. What do we reach? It's something we have to find the time domain equation for. The general format of the time domain equation is going to be K0, so V output of T. This is V output, right? And 240. It has nothing to do with op-amps, right? So the output voltage across this is equal to the current flowing multiplied by the current. The voltage divided by the impedance, or the current multiplied by the impedance of the circuit. So V output of T is K0 plus K1 e to the minus T over tau.
But isn't it's DC, right?
We have to find the general format. Yeah, it's DC. But what we have to find the general? Yes, it's the DC source. Again, it's like you remember your 214. You put a DC source here, and you put a switch, and you close the switch at t equals 0. How do you find the equation for current?
Just before the switch.
Right after the switch is closed, you want to find an expression for current, and then find the corresponding output voltage that is going to be developed across this capacitor. Because when you have the corresponding output voltage across the capacitor, that is equal to negative of the output voltage across the op-amp terminals. Right? We know at steady state what happens from the transient response, from the...
T is 0, V not initial value, right?
Yeah, so at t equals 0, let's substitute at t equals 0, what do we know? What do we know about the circuit? At t equals 0, e to the 0 is equal to 1, right? E to the 0 is equal to 1, so the output will be K0 plus K1, right? V0 of 0. What does this tell us? So how about V output of infinity?
No, it's 100.
E to the minus infinity is 0, right? E to the minus infinity is 0 plus K0, right? We know that about the circuit. So what do we know about V output of infinity?
It's equal to 100.
It's equal to 100, So V output infinity is equal to 100. So K0 is equal to minus 100.
Why is it minus?
So
It's not.
K0 is equal to 100. 100 or minus 100? Yeah, the VC, the output of the capacitor. Sorry. This is let's put this in VC so that we don't confuse VC and V output. V output is the one for the op amp. Okay, so let's write this in terms of VC. So VC is equal to K0 plus blah blah blah. So K0 is equal to 100. Right? So, and if I take this K0 equals to 100 and substitute it here, so this is equal to 100 plus K1. At t equals 0, the capacitor voltage is equal to 0. Right? I said that the initial condition of the capacitor voltage is 0. So what does this mean for K1? K1 will be equal to negative 100. So at t equals 0, the VC is equal to 0. I assume 0 initial conditions. For 0 initial conditions, K0 plus K1 is equal to 100 plus K1. 100 we got it from the K0 here. Now we want to calculate K1 because I want to substitute in this format. I know that the output will fit this format because it's a single time constant circuit. It's a circuit with one capacitor. The circuit with one capacitor has output voltage equal to K0 plus K1 e to the minus t over tau. That we know. How do you calculate V1, K1 and K0? That is from your circuit conditions. So the two circuit conditions we know about are these two. V at 0, V at infinity. We're able to calculate 0, K0 and K1 from that case. So K1 is equal to minus 100. We're okay with this? So if that is the case, and this is VC, not V1 output, right? VC. I assume that that's an assumption from your transient response. I assume that from your transient response. Yeah. So if that is the case, the equation will fit this format. Yeah. If it does not equal that, then K0 will equal something else. Right?
I'm confused because back in ACM 14 we
Yeah.
used to call K0 like V0 and K1 like I don't know. But what are they called right now?
It doesn't matter. They're just two constants. They're just
It's easier to find V0 at infinity, VC at infinity, and VC at 0, and then just plug it in instead of doing.
Yeah, you can find this equation whichever. You can go review your 214 material and find this equation whichever way if you feel comfortable. I have no problem with that. Yeah. Right. So that's.
And we used to first determine if it's a step response or a natural response.
No, but this will not change this equation. Yeah.
Yeah, this is a step response.
Yeah, but why will it? It will not change the equation itself. I mean, the output you will substitute. Okay, so we calculate the equation for VC. What V output is equal to minus VC of t. Correct. So VC of t is equal to K0, which is 100 minus 100 e to the minus t over tau. So V output is equal to minus 100 plus e to the minus t plus 100 e to the minus t over tau. So I can take the minus 100 outside as a common factor, and I will have 1 minus e to the minus t over. Excuse me. The output of the op amp. Now remember, all of this was without the op amp, right? Everything we did here had nothing to do with the op amp, right? But is everybody okay with what we did here? You're okay with what we did here? Okay, so now let's relate it to the op amp, right? So if I want to relate it to the op amp, I know that my op amp circuit looks like this, and this is my V output, this is my V input, and this is ground. So I know that V output plus VC that we derived before is equal to 0. Since I have feedback, the voltage difference between these two nodes is 0, then V output equal to minus VC. VC was equal to, V output equal to minus VC is equal to minus, VC was equal to 100 minus 100 e to the minus t over tau. So the output is equal to minus 100, 1 minus e to the minus t over tau. Tau was 10, right? We calculated tau was 1 mega ohm was R, and the capacitor was 1 nano farad, right? So tau
Oh,
was
it's 1 over 100, so it's going to be 100.
no, it's C times RF is equal to 10, that's according to what they have here. So it's C was equal to
10 milliseconds.
C is equal to 10 nanofarads, and the resistor is equal to 1 mega ohm. So 10 nanofarads, 10 times 10 to the minus 9 times 1 mega ohm is equal to 10 milliseconds. Okay, so this is 10 milliseconds. If time is in milliseconds, I have 1 millisecond here, which is my input square wave, then this will be 10. So this is minus 10 over 1 minus t to the minus t over 10. Okay? If you substitute here, you will get, for V output at 1 millisecond, you will get minus 9.5. Do we see what we did or no? Everybody's okay with this? Because my square wave is for 1 millisecond. Now I have my input voltage here that's a square wave. It's a pulse that has a duration of 1 millisecond. Right? So I saw the effect of voltage on this RC circuit. I calculated the time domain response. This time domain response is the voltage across this combination. This combination happens to be the negative of V output. So V output equation is now this. The objective is to draw. Initially, we drew the output voltage without the resistor in the back, in the feedback. At 1 milliseconds, we saw that the output voltage ramp moved from 0 all the way to minus 10 volts, right? And then, if the pulse went away, if the pulse was brought down to 0, still without the feedback resistor, the output voltage goes down to 0, because the output voltage was what? Was a constant times t with a negative sign. The output of t was this. In the case without the resistor. In the case with the resistor, it's this. Right? So in the case without the resistor, it's this. So what happens when the voltage becomes 0? At 1 millisecond, the voltage became 0. I get 0 at the output. Right? So this is V output over V input. Right? So the voltage became 0. So actually, no, the V input was here. Right? It was V input over RC times T. Right? That was the value of the V output. Correct? Now I have a different expression for the output voltage. What do you think the output will look like? We said that at 1 millisecond it's going to go to, instead of minus 10 volts, it's going to go down to minus 9.5 volts. Guys, come on. Why? Because we substituted here. We substituted, if you look at the substitution here. So this is the output voltage equation that we derived. So if you substitute with t equals 1 millisecond, the output will be minus 9.5. If you're okay with this equation, then it's just a direct substitution here. Okay, so it reached minus 9.5. It was minus 10. It was minus 10 at 1 millisecond. And now, if I kept the square wave at the input, what's going to happen to this? It will just continue. Correct? Since I have a square wave ending at 1 millisecond, it stopped here, and the output looks like this. Now, if I add the feedback resistor, what's going to happen to the case with the capacitor what's going to happen to the case with a very large feedback resistor at 10 milliseconds? At 10 milliseconds. Assuming this pulse was kept for 10 milliseconds. No. Why? This pulse is at 10 milliseconds. If it was without the resistor, this will continue
Minus 100.
across the straight line,
Minus 100.
right? It will go to what did it go to? It's minus 10 times 10 is going to be minus 100. So this will go to minus 100 volts at 10 milliseconds. 10 milliseconds. Also, if I have my resistor in the feedback, and I keep the pulse for 10 milliseconds, what will the output be?
It's going to be
Also minus 100, because the time constant of this circuit, guys. Remember the time constant, I kept my current. If I keep my current in here for as much time as required so that the capacitor reaches steady state and becomes an open circuit, that happened after 10 time constants, right? And each time constant was 1 millisecond, right? So, after it happened at 10 milliseconds. At some point it happened at 10 milliseconds. So at 10 milliseconds here, this capacitor became an open circuit, and the voltage will eventually be the same as you have here, as minus 100. Because if the capacitor is not there, the gain will be determined by R2 over R1. Okay, it will be an amplifier, inverting amplifier with gain R2 over R1. Now I have this resistor in the feedback path, and we derived an equation for the output voltage. If I substitute it in the equation, I get that at 1 millisecond, I have an output voltage of minus 9.5 volts. That's what happened here. After 1 millisecond, the voltage became 0. Without this resistor in the background, the voltage would have fallen straight, right? Because I have this resistor in the background, how will the voltage fall? It's eventually going to fall, right? It eventually has to fall. Because, okay, without the resistor, it fell, right? Without the resistor, it fell. So the resistor was open circuit, right? I mean, you have to always think that the resistor was there, but it was very, very large. Now I brought this resistor from infinite value to 1 mega ohm, which is still large, right? So if it's infinite value, it will fall down to 0, like the case for the capacitor case, right? If it's 1 mega ohm, instead of falling to 0 quickly, it will fall down with a certain time constant, exponentially. But the output voltage is still guided by the exponential equation. How is it going to rise? Is it going to rise the same way as the case where R was infinite? Obviously not, because after 1 millisecond, after 1 millisecond, you should have noticed this one. After 1 millisecond, the case with the resistor, the voltage became 9.5. Right? At the same 1 millisecond. Right? So it fell after that exponentially. Do you think it started from 0, and after 1 millisecond this was a straight line? It wasn't. It was an exponential it was the same exponential that we had, it's the same exponential equation that we derived. I cannot draw it as an exponential, but the output voltage will basically be guided by this exponential equation. We know that at 1 millisecond it's minus 9.5. How does it rise? How does it go to minus 9.5? It's an exponential function. Right? So and it's close enough to the ramp. Right? So I don't know, I spent so much time on this. Shouldn't. 1 millisecond minus 10. This is a straight line. Assuming it's a straight line. 1 millisecond red. What happened? Minus 9.5. From here to here is guided by that exponential equation that we derived. The blue was going to fall to 0 after 1 millisecond right away. The red will fall to 0 eventually, but exponentially, guided by that output equation that we have. Is it okay now?
It can never like be
Huh?
minus 11 or minus 12.
Minus 11 or minus 12? I mean, it's. I mean, we have to crunch the numbers, but I don't think it can. Yeah. Because you had a time constant. You had your time constant of the circuit is RC. R was infinite, basically. So what? And now it's finite. No minutes. There was no. Yeah, if it falls, it will rise slower. Right? No, it will never. As long as you have a time constant, what's going to happen? It will rise slower. If you have a time constant, it will dictate how fast you rise and how fast you fall, right? So before we were not. Before the circuit was not. The output voltage equation was what? It was minus VI over RC, right? Our input, not the feedback resistor, times T, right? There was no time constant yet. So the circuit, the voltage was not right. So this is the fastest that it can rise and the fastest that it can fall, right? But now the voltage is, minus 100, 1 minus e to the minus t over tau, right? So it's gonna be controlled by this time constant. So this will definitely be slower.
But if you look at the graph, it's a straight line.
I know, because it's not straight line. No, it's not. If you look at the graph here, it's not a straight. It looks like a straight line. This is a straight line, but this is not. This is like, again, has some exponential to it. Yeah, exponential shape to it. It's very subtle. It's very subtle, because the resistor R was 1 mega ohm. Try to redo this if you want, and use a resistor R of 10 kilo ohms, and you will see the difference. Right? Okay, so this is an example of using the integrator circuit to create basically a triangular waveform. If you see what's happening here, I put in a square wave, and I got what? Something that looks like a triangular waveform. Depending on the value of R and C, I can make this look more like a triangular waveform. So this is just an example application of what the integrator can be used for. Okay. So any questions on integrator? Okay, how about differential? Let me just change the place of the R and C. So for the integrator, we had the circuit like this, plus, minus, and we had the R here, and we had the C here, and this was grounded, and this was VI, and this was V output. We said that current flows here, and then the same current flows here. This current is equal to VI over R. This VI over R flows into the capacitor, meaning it becomes the capacitor current. So capacitor voltage is equal to 1 over C integral of IC dt, and we said that this is 1 over RC, so it's VI over RC integration of 1 times dt, right? That was capacitor, and V output is equal to minus VC, and that's why we call this an integrator, because it's integrating in the time domain. It's integrating the VI is in this case is the DC, but I can keep VI as a general voltage. I can keep this VI inside as a general voltage. What's happening is I'm taking my, actually it's better to do that. I'm taking my voltage signal that is at the input, and I'm integrating it with respect to time, right? That's what I did here. I took my input voltage, I integrated it with respect to time, and at the output I get the integration of that voltage with respect to time. So if I flip the place of the capacitor and the resistor, yeah. So if I flip the place of the capacitor and the resistor, this is VI, ground, the output. So, but again, I have feedback. Since I have feedback, what is the difference between these two?
So,
0, and since this is grounded, then the voltage here is also 0.
The current flows.
What?
So the current from VI flows to the resistor. So you just use it like you did before. You just use impedance.
The current from VI?
Just flows through. It doesn't go to the.
No, there is current here. Since I have voltage here,
There is zero current
and
in the
there's
amplifier, so it goes up the current.
exactly this same current flows here. What is this current equal to? It's the current through the capacitor. Current through the capacitor equal to IC equals CdV input by dt. So this is IC equals C dVc by dt. What is the voltage across the capacitor? If this is 0, then it's equal to VI. So basically I'm differentiating my VI, and that's the current flowing here through here. This current is multiplied by resistor R, right, over here. So then V output is equal to minus VR, right? V output is equal to minus VR,
Which is CdV.
which is equal to minus this current multiplied by the resistor. It's this resistor here, R, multiply by the current that I put through it, C dVi by dt.
Just that. That's what
Huh?
I'll see.
Minus R, yeah, it just happens to be because it's any circuit that has single time constant will have a time. Any circuit that has one capacitor will have a time constant, and that time constant will be equal to the resistors in parallel with the capacitor if you ground the voltage sources, which is what we did before, right? Ground this voltage source, right? And ground this voltage source. This capacitor sees this R across, right? So it will, any circuit with a R and a C will have a time constant. Okay, so this is what happens here. So I'm differentiating my input voltage, multiplying it by a scaling factor. Right? So this is what we're going to do next. So again, here they start with in general it's minus, V output over V input. The gain is equal to Z2 over Z1. Z2 is equal to R. Z1 is equal to 1 over SC. So the SC goes to the top, and the negative sign comes from the fact that it's a inverting amplifier configuration, right? So this is my transfer function, and we derived the equation in time domain. What's the problem with this one? Remember, the integrator has infinite gain at DC. How about this one? What does this look like? At DC, it will have no gain. So how about, which means I cannot differentiate, of course I cannot differentiate a DC signal. If you differentiate DC, it becomes 0, which is fine, so it works there. But how about its response to very high frequencies? What will this do to very high frequencies? What's the magnitude response at very high frequencies? Canvas, desktop. What's the magnitude response at very high frequencies? So at DC, it's 0, right? So we know that at DC, at low frequencies, it's 0. At high frequencies, the magnitude will increase with frequency, right? So we know that it looks something like this, right? And at magnitudes of frequency going to infinity, the magnitude will go to infinity, right? Do we agree? So it's going to look like this straight line. Where does this straight line cross 0? So when the magnitude is 1, when will the magnitude be 1? At omega is equal to 1 over RC, right? So at 1 over RC here, the magnitude in dB becomes 1, meaning I have 0 dB here, right? So at omega is equal to 1 over RC, I have a magnitude 0 dB. At omega greater than 1 over RC, the magnitude increases. At omega is infinity, this magnitude becomes infinity. So same problem we had before for the integrator. What was, sorry, same characteristic we had before for the integrator. Integrator characteristic was the opposite, right? At DC, the gain was infinity. And at high frequency, there was a point where this gain becomes unity, or 0 dB, right? That was the integrator. What did we find was a problem with this? That if we put a DC signal, what happens in the integrator? When we put a DC signal, what's going to happen? The gain will become infinity. So the signal, the output will go to infinity. What does that mean for the output of the op-amp? It will saturate. So what did we do to solve that? We put a resistor in parallel to limit the gain at high frequencies to some value. I limited the gain at low frequency to some value, and then have attenuate everything after that, right? Why did I do that? So that allows me to put a DC into the integrator and be able to do my work. If your signal happens to have some DC content, you want to be able to have a limited gain to that content. You don't want something to go in and go out infinity, uncontrolled, right? So, but if you're able to control it, then you have a result, right? So your signal will not be clipped. You will be able to transfer your information with a large gain, but not clipped. If you clip the signal, if you have a sine wave that's supposed to go through as a sine wave, but you clip it, then you lost information. But if you make it as large as possible, then you know it's still a sine wave. You don't lose information, right? So, and that's what we did for the integrator. We added the resistor and the feedback so that we can create something that looks like a low-pass filter and be able to control the gain at low frequencies. Same thing with the differentiator, right? Except that the differentiator will cause some bad stuff happening. So here, high frequency. So the high frequency signal is something we cannot control its gain. So what do? We want to limit or control the gain at high frequency. So we will do something, obviously, that will do this. What will do this is a resistor in series here. Because I cannot put a capacitor in the background. If I put a capacitor in the feedback, then it will not work. I mean, we can derive the transfer function, but basically it will not work.
And then it's going to look like a high pass.
Then it looks like a high pass filter, right? But what happens to, but the bad thing is anytime you have, a reasonably high frequency content, I'm amplifying it too much. So anytime you have a signal like a square wave. Square wave includes steps. There's impulse functions. These impulse functions have infinitely high frequency. So what's going to happen to these frequency content? Always be amplified. So even though, for example, let's say you have a ramp that rises very fast, right? What's the differentiation of a ramp?
Horizontal line.
A horizontal line, right? So the problem with if you put this through a differentiator, what's going to happen? The very high, the high frequency content of this ramp will be amplified even further. So the problem, again, let's say this ramp has, you do this and then you do this, for example, and then go back here. This is extremely high frequencies. These will be amplified and they will saturate your output. So it's practically fine. I mean, you can limit it. You can limit the gain like we did with the integrator. You can do that. The way you do that is, as they show in the textbook here, by putting where they don't draw it. Oh, they don't draw it, but they say, I think it's here. They say it here. Here. It is usually here. When the circuit of figure 2.27 is used, it is usually necessary to connect a small valued resistor in series with the capacitor. Right? This modification unfortunately turns the circuit into a non-ideal differentiator. So what we discussed today was the ideal integrator and the non-ideal integrator. And then the differentiator, the ideal differentiator and the non-ideal differentiator by putting this circuit, the resistor in series here. They don't have that and they don't analyze that in the textbook here. So we'll stop here, continue from here next time. I was hoping to finish, but
Oh, no, we did it.